The same thing's on 290.
Oh, you did? Okay, there you go. So I put on my seatbelt and no, I'm kidding. Anyway, so thanks for coming out, guys, on Valentine's night. And the first thing that I was going to do, I do have a agenda that Terry has got. He's going to display for me. But the first thing was to welcome visitors. And
what about practical astronomy?
That's
what we need to be.
It's visitors is before the business meeting. Okay.
Yes, right.
All right.
I
So
don't think we have any visitors anyway, but
I was gonna say that. So
maybe we will by the time we
online,
start
maybe.
that.
there could be some folks on Zoom, but all right. So yeah, sorry. I'm a little out of it. So we've got practical astronomy first from 7 to 7:30, and where is he? Oh, there he is. Hey, Jeff he's hiding. Jeff is gonna do a presentation, so take it away. Thanks.
Okay, practical. So this is the junior astronomy display I'm taking to events now, star parties and inside events at schools. This all started by going to star parties and sitting around and listening to preschoolers ask me questions about black holes. I realized that there was a need there that we could fulfill a little bit better, give them a little bit of stuff to talk about. So I went online and started Googling and searching for materials to make some kind of a black hole demonstration display. And in doing so, I found the motorized solar system here that projects the images of the planets, and you can click through them here, which is an attraction in itself to most kids. They like to mess with it. And then this moon in my room just like came with this moon here that just shifts through the phases automatically, and the little graphics here explain something about the phases and eclipses and that kind of thing.
That's really nice.
So then I came up with the idea of putting in a box, and I was gonna have to, at some point, I'm gonna have to put lights here, some red lights. So I needed a box to hold the battery. And then I've got a red filter in there because this is too bright at star party, so I put a piece of red film over it. Let's see what happened next. So then I got more people involved. We started the junior astronomy subcommittee. That included Swetha, Susie, Greg, Joyce, and Dawn. And so we started kicking around ideas of what we could do. There's a kickstart here. Kicking around ideas of what more we could do. And we came up with a whole lot of ideas. So we started with star charts. Shwetha came up with that idea to print out these individual constellation star charts and then hand them out at the parties to kids so that they could use them and look up at the sky and find constellations. So I took some of those out in my backyard, and they just really didn't work too well. So then we came up with the idea of putting a glow-in-the-dark star stickers on. Shwetha bought some and stuck those on. And then we tried those, I think, at one star party, and it was a really busy star party, so we didn't get much feedback on that. So I started messing with those out in my backyard, and Shwetha figured out that I tried sticking them all under lights in my room for the whole day, and then there was going to be a star party that night. So I loaded them up, got them to the star party, all the kids were there, I took them out, and they weren't going at all. So not being radioactive with material, apparently they don't really hold on to glue very well. So Shwetha came up with the idea of using a UV flashlight to light them up, and they light up really quickly and they hold on pretty good. So you could do it at the star party. So the first time she tried that, they just ate them up, took them all home. We're really excited about it. And so as over a period of time, then I came up with this idea that they ask a lot of questions. People ask a lot of questions about the life cycle of stars. So I found one that was really simple online and then just blew it up and made it into a little display. Answers a lot of people's questions about stars.
Yeah, that's great.
Mm-hmm. So over time, we kind of watched it, and the main idea we settled on is more of a self-serve display situation because the number of volunteers is very variable. And to do a whole lot, you need volunteers. Now, when volunteers are manning this, or staffing this, shout out to you too.
Thank you. I noticed that. Thank you, Jeff.
They talk them up and, explain what they're for and how to use them. And they just, we can just get rid of them all real quick. It's a little slower than that when there's not any volunteer staffing them. I also noticed over a period of several star parties that many adults were using these. And many adults had questions, and many new members had questions on how do you find objects in the sky. They didn't know. So I got a little more elaborate on some of them. Some of them are just single constellations like this one of Orion. And some of them are areas with the brighter DSOs in it for adults that use telescopes. You can take them home and use them in conjunction with a star chart or your phone app or planisphere to locate some of those DSOs. So they seem to be pretty happy with that. And so now at any kind of event, it's pretty much halfway even between kids and adults that are interested in it. So I'm thinking that may evolve a little bit further into providing some type of area more in-depth diagrams of DSOs. There was one fellow at a star party. He and his daughter came over, and I was sitting at my telescope, and there weren't any volunteers over at the demo scopes. And then this table was a little further on with these star charts sitting there, and he asked me for help finding M31. So he was using this star chart right here to try to find M31. So I knew the general position of it. And he had one of the telescopes, the demo scopes there, and he couldn't quite figure out what he was looking for. So I gave him the keyword of faint fuzzy. That's what you're looking for. So you can point the red dot finder in the general area by using one of these charts, and then use the actual 3 to 5 power finder scope to locate the faint fuzzy, and there it is. A light bulb went off in his head, and he sat down with the telescope, pointed it out, saw it. Oh yeah, that's what you're talking about. And they found it just like that. So it's kind of leading to kind of a really introductory how-to printout sheet of how to get you from, you've never used a telescope before, you've never really found constellation before, to finding these DSOs in the sky. And so far as new projects we're working on, I'm still working on that black hole display. I'm thinking about a very weak vacuum with inside of a plexiglass case with some dry ice, I was sucking it down the hole and then spitting it back out. And then what was the other one? The telescope, cutaway telescope. I bought a couple of inexpensive telescopes that I was going to cut away the outside of it and make it kind of hinged to where people can open it up and look in there and see the mirrors and such. But those little ones, those little cheap ones are a real hit with the kids at these inside school events, because they can maul them and turn around and mess with them, and it's not really, nobody's getting upset, So they like that, stick their hand down the tube.
You're not supposed to do that?
That's about it. Any questions?
I just like to say, Jeff, that I think that what you said about this being great for adults, beginning astronomers, because when I think back 20 years ago, when I was kind of a beginner. I mean, I had taken some astronomy but still there was a lot to learn, and I taught myself a lot of this stuff. But to have an organized way of somebody else, and by reading and websites and that kind of thing, but to have an organized program, somebody who is another astronomer who is teaching it to adults, I think is a great idea.
Right. That's kind of what I'm drifting towards in my presentations. I had started by trying to teach people, because they didn't have any, we gave them a star chart, but
Yeah.
they don't really know what to do with it.
Well, I will say, we try to explain it at
Oh.
the welcome table.
Oh, okay.
I mean, some
Okay.
people will accept our explanation more than others, some would just grab it and go, but
Right.
we do attempt and, you know, around the circle, it also tells how to do it. That in itself is not enough, but that's
Right.
starting.
So I think we're working in the same direction then,
Yeah.
is try to, my latest presentation redo is geared more towards the laser show, with a star chart showing them how to, you know, use it to actually find one constellation, whatever constellation it is, it's easiest to find, and then go from there to find everything else. So, and then work towards a printout, like you suggest, that gets them. Because I do have a printout sheet of website where you can buy planispheres, where you can download free star charts and print them out. The phone apps and like Norton Star apps. Well, I've had several AAS members walk up to me and ask, how do you find stuff? How do we find stuff? And I remember that's what I had was a Norton Star app. To find the DSO, that's what they're looking for. They can find the constellations okay, but they don't know how to look or how to find those things. So I'm thinking some kind of consolidated printout, full sheet, 8.5 by 11. It's got QR codes for the website addresses, so they can just do it right there and see, you know, see some stuff. That explains all that a little better. And then also my presentations, I'm working towards getting a little bit more involved in that. Show them how to find the DSOs, what to use. It takes me a while to connect everything up. Using the started with the star charts, started pointing out constellation and just telling them use your star chart, and then trying to explain how the star charts work, how do you actually use a star chart, and how you got to turn it as you go around so that direction is always pointing down. And then using these are very helpful just on one, you know, so they can look for, you know, what they're looking for, the SDA objects. That's typically what's listed on them. So anyway, it's a evolving thing.
Yeah, does anybody ever ask you about your setup besides nosy people like me? Like, how does that all work? You know, you've got a camera in there and everything, you know, it's like some people might find it interesting. I do.
Oh yeah. Oh yeah, there was a woman at the Pflugerville Star Party. That was standing around watching everything I was doing for a good 45 minutes. Asking questions, you know, what are you doing with that? What's that? What do you do that? And she wanted to replicate that system.
Okay.
You can tell she was very intelligent and really was into astronomy, and she wanted to do it, be able to see that kind of stuff.
There are certainly people who, when we have the Sea Star at the welcome table, they want to know how that works.
Yeah.
So,
Yeah.
and that's a whole lot simpler, but yeah.
Yeah,
Well,
well,
the
that's
kids are
like,
always fascinated with my,
Exactly.
my iPad sitting in my chair
yeah.
while it's imaging. Yeah, like there'll be 10 of them around it, just staring at it.
Right.
Staring at the iPad.
Well, when they asked me, one of the first things they asked is, how much did that cost? I tell you, we thought it was like, you know, $50,000. But then I tell them about a Sea Star.
Yeah.
You know, it was $500 and they'll get one of those.
Hello, I'm on Zoom. Can you hear me?
Yes.
Yeah.
Hi, my name is Bill. I just wanted to tell you, I applaud your effort, your creativity, your attitude about this whole thing. I think you did a really great job of just communicating so many things to the people with the AV, shall we say, techniques. So I think you did a great job. Thank you.
Hey, Jeff. A thought just kind of occurred to me. So last night at the school event, one of the dads was asking me several questions about kind of like ideas for like a first telescope, and even at public star parties, people do. So I wonder if we had just a little printout with 4 or 5 kind of budget friendly like suggestions for kind of first options for a first telescope.
Yeah, that's a
If
good
people
idea.
ask.
That's a good idea. Yeah, because you know, you can't really explain something from a point of view very well of a lot of knowledge. because there's always gonna be something that you assume that who you're trying to explain it to already knows. So that's what I'm kind of uncovering by going to more and more Star Party. If more and more people ask these questions, I'll go, oh, okay, so that's, yeah, I see where the disconnect is. Well, that's a very good example of this.
Have you
So-
ever done after photography, presentation?
I don't know how to do after photography.
Ah.
What's that?
So, well, as one of our,
I
as one of our practical astronomy lectures like you're doing now, a one on astrophotograhy, have you done one of those?
Well, I'd rather do one on EAA,
What's that?
electronically assisted astronomy, which is what
Oh,
my sister
okay,
did.
okay.
I've been preparing, working on a big presentation for that, but practical astronomy would be just as good. Okay.
Yeah, we've got quite a few very talented, capable and experienced digital astrophotographers. And we could do several things that people are interested in. That's why you don't need to hear from me until I've got some idea how to get something. I have to use the algorithm. Hell, that's way different.
So anybody that wants to volunteer for the junior astronomy subcommittee, or there's a lot, as you can see, there's a lot that you can be doing at Star Party. Volunteer wise, I set up 3 demo scopes that the public can use just in front of this table, and they sit there, and those are very popular. People are going around to them. Of course, they need some training on how to deal with them. Typically, what I do is during my presentation, I tell them where it is and say that you can use them, and I'll give a short training session after I'm done with the presentation. Of course, I never make it over there, and they're wandering around on their own trying to figure out how to use them. But those telescopes are club scopes, and they're very user friendly, and they really can't hurt anything. So it's not a big deal. So if we have volunteers there, they're busy all night long explaining to people how to use them and what to look at.
So what are those scopes specifically?
We've got the 8-ounce, one of those Orion 8-inch Dobsons.
Mhm.
And then we've got a Meade, looks like about a 5-inch Mac.
Mac?
Yeah. And then we've got the about a 5-inch Meade refractor.
Wow.
A 5-inch refractor?
It's big refractor.
Well, it's bigger than a 3, you know, maybe it's not quite.
Smaller than a 6.
Yeah, somewhere between 3 and 5.
Okay.
But the problem, the main problem is getting them to where they don't touch the
Plans.
finder scopes. I took all the knobs off because you don't want people messing with those knobs.
So besides the Dob, are they equatorially mounted? or-
No.
Okay.
The Meade is actually they're all dad.
Okay.
Easy to go find.
Yeah,
Good reason to learn how to start.
right.
You're gonna
So,
bring some of this stuff to Girl Day, right?
Yeah.
Yeah.
Yes. Right, in case anybody's interested, there's gonna be a subcommittee table tomorrow at the open house event where people will be sitting around making these. Because you can imagine sticking glow stickers on these things in any quantity is tedious and boring work.
Oh, no, not if you love stickers.
Okay.
you got one. So, are you reaching your capacity to carry all your stuff with you?
Pretty much. I'm thinking about a display, what was the other display, a display similar to this, just a breakdown of the 2 different types of telescopes and how they work. So just a real quick thing. And then if I eventually get to the cutaway telescopes, those are very small and easy compact. I can probably fit those in, but beyond that, I'll have to start seriously thinking about not taking my telescope to sit up.
So a covered trailer is starting to sound good.
Yeah, actually, I thought about that in a positive light for the first time.
Everything lives in that and then you just hitch up and haul it away.
Well, right now I've got it all in the back of my truck and it stays there for the duration of the Star Party season. But I do have to unload and load depending on what's going on. All right.
Hands up online. You know, I was thinking it'd be fun. I think we have some old kind of dead 8-inch Dobbs. Right?
Dead?
Yeah, chainsaw tomorrow. Let's make
Oh.
a cutaway Dobb tomorrow. That'd be awesome.
We've definitely got a couple of dead 4-inch reflectors
Yeah.
sitting in the storage now. I was looking at those and those will never make a real scope.
Oh, okay.
So if you want them,
Yeah, I'll look at that tomorrow. They're at 512.
yeah,
Okay. Yeah.
I'll point them out to you.
The demo, cutting them
Oh.
open tomorrow.
So one last thing I want to throw out there is that, Susie keeps mentioning some kind of a contest, and we've been trying to figure out how to work it in to the star parties. Because, and the problem is that we don't want to depend on volunteers to run this contest. So the idea I had was to make another sign like this, just sitting out to the side, saying contest. Point out, find the constellation. How many constellations did we find? So people come along, especially kids, and they grab these up and they try to find them. So when somebody finds some, and we can have a delineation of how many for whatever prize, they get that prize. And they come over, find a volunteer and say, here, this is the ones that I found. Okay, you did. This is the prize you get. So my idea, just off the top of my head, was, you find 5 constellations, you get a $40, $50 telescope. Maybe some of these old telescopes that we don't have any use for. Another idea is a free year's membership in AAS. So that's kind of where we're at working on that. Some type of contest that they can use. All right, thank you very much.
Thank you.
Thank you, Jen.
Brian, I don't think you heard my suggestion of using a chainsaw tomorrow to cut open one of the gobs for a cutaway.
Oh,
What do you think?
I've got one of those big sawzalls, I've probably.
Oh, yeah, follow on.
Saw everything, how are we gonna handle it?
Oh, okay,
It's sorry about the first one.
yeah, yeah. I'll be thinking.
I got it.
It's slow. Okay.
No, tile saw's done.
Anybody have any comments or anything about that? That's pretty awesome. I did notice that Mercury is gonna need some new Einsteinian equations because it was really wonky as it was going around, so.
I noticed a lot of pausing in this moment.
Yeah, something new is going on.
Jupiter and Saturn are really sticking together, and I happen to know that Saturn was very slow.
It's that dark energy, dark matter stuff.
40 and
You
50.
can count on a physics student to come up with that.
What'd you say, Bill?
I say we can count on a physics student to come up with that.
Oh,
Yes, you can.
yeah, astronomy. I'm having to take physics, but not, it's just glorified math. It's just gussied up math. Okay. Is our guest speaker on yet? But I don't think so.
What would their name look like?
Oh, it's Dr. I don't know how to pronounce it for sure. Molyneux. I'm gonna guess. But we'll find out when.
Don't think so yet.
Okay, that's good. Okay, well, I guess we can go ahead and start our business meeting, and we like to keep it, kind of brief, short, so that we don't make the speaker wait too long. And Terry, if you could bring up the Deathless
agenda.
Crows, that is the agenda that I put together from last month's agenda and made a couple, maybe I added a couple words, but it's glorious. Okay, and the first thing, the first thing we do, okay, Joyce is a second down. She just went to the little girl's room, is welcome any visitors. So we've had a few more people come in since we started our practical astronomy. For the folks just getting here, we had our outreach chair, Jeff, do some demonstrations of his constructs that he's using at star parties to explain astronomical concepts to people, to kids, to adults, to everybody. So it's pretty cool. I'm impressed. So yeah, are there any visitors here tonight in person here? First, I'll ask. No, okay. And then any visitors online? Okay. Yeah, a lot of diehards here in both places tonight. Because it's a special day. It's Valentine's Day. And the weather's pretty crappy. So tomorrow I heard it's supposed to be nice tomorrow, so that'll be exciting. Okay, so let's go ahead quick. I did the visitors part, so let's jump right to treasurer. So Charles.
All right. So, for anybody who's interested, these are always in the Sidereal Times, but we had a pretty big expense in the month of January. It was our liability insurance for the year, $856. So that's kind of an unusual expense. So I thought, well, we're not going to do as well this month. Well, lo and behold, it always surprises me. We actually had so much more income than expense that our net gain exceeded. It's been running around $700, and this month we had over $1,000 in our net gain. So that was pretty impressive. If you look at all of our cash accounts, our total cash balance is $44,791.43.
Yeah. Okay, you got a few pennies to rub together. That's awesome. Thank you, Charles.
You bet.
And Joyce is here. Do you want to go ahead and do your vice president's report?
Yeah.
Yeah. Awesome. Even as. Yeah. Well, this is nice. I see that you and I aren't the only females here now.
No, one more, no.
Yeah,
There's two
right.
more.
Another lady.
Oh,
Yep.
there's several.
There's
Yeah, there's
three
several.
more. Awesome.
Yeah.
Thank you guys for showing up. I remember when I was a computer science student years and years ago, and I was the only girl in the class, and the guys were like, "Oh, that's cool." And I said to them, "How would you feel? You were sitting here," and it was all women, all girls in the class, and they're, "Oh, I didn't think about that."
I don't know. I wouldn't be surprised they'd be happy.
There is that.
Well, there's not really much to report that I haven't already said. We have programs established for almost every month of the year, and I'm looking forward to all of those, and that's pretty much it.
Awesome. And how do you pronounce our guest speaker's name? Is it Molyneux?
I think it's Molyneux, but I'm not sure. I was going to
Yeah, we'll find
pronounce
out.
it that way and ask her if I was right.
Yeah, there you go. Take some stabs at it. Okay, thanks, Joyce. And then, I don't, who's next? Wants to go next? For our reports. I feel bad that I don't remember, but evidently nobody else does either. Oh, there we go. Yeah.
Sean for communications.
Are you guys just starting?
Well,
Yeah.
business, we'll have the program in just a little bit.
Yeah, the speaker hasn't started. We're just doing a quick business meeting.
Next up is Sean,
Yeah. Sean.
and I don't see him online.
Okay, well then, equipment chair Ernie, is he online?
No, I don't think so.
What? That's it. We're gonna cancel the meeting.
Yeah,
Okay, well, I guess everything is going swimmingly, so, and I don't remember what they said at the EC meeting. That was 2 weeks ago. Okay, well then, member services, our chair is right there.
okay, it devolves to me. So I'm not exactly sure of the date, but we did hold a member star party at Bad Wolf about 3 weeks ago. Maybe it was still in January, I guess, towards the end of January. Very nice night for observing, except it was very cold. And we had a lot of people come out, about 15 altogether, in that environment. Some didn't stay very long, and some didn't show up until 10 o'clock. But altogether, it was kind of nice to get back out there again. As far as I know, all the infrastructure works, and Alan was out there with us. Now, we were also planning to do a star party on the 22nd of this month at Bad Wolf. I'm not going to be able to host it, and the weather forecast, long-term forecast, still doesn't look very good for next week on the end. So I'm thinking of maybe canceling that and putting all our energy into the member star party at Pedernales for March. Now, what we could do, and I'll ask Alan about this, is I could just put out a letter that says we're not going to have a hosted member star party at Bad Wolf, but if several of you want to get together and come out, just get with Alan and
If you want to go out there, that's not a problem.
and go for it.
Anytime. Awesome. Okay.
The other thing that's up is we will be having our open house at area 51.2, as Greg wants to call it. So our storage facility. We've had about 33 people reply to the invite. Slightly more people than I'll probably or might show up. There'll be about 7 or 8 of us officers there. A lot of people are planning to bring scopes for scope clinic. We even have a couple of people that are going to drop off scopes there, donate scopes there. So
Cool.
that's about it.
Okay, awesome. Well, thanks so much, Terry. Appreciate it. And then next we'll hear again from Jeff, our outreach guy, who is demonstrating all of this.
Outreach, for January, we didn't do any, public star parties.
Yeah.
Not much to report on that. In February, we had a star party on the 1st at, Veterans Falls State Park. We had a star party on the 7th of February at Pflugerville, which was actually our first real full-length star party. It went over really well. And then we've got we had a award last week. We had 2 weeks ago, we had a inside school STEM science fest at DeSal Elementary in the Pflugerville School District. And yesterday we had the same thing at Spring Hill Elementary in Pflugerville. Apparently Pflugerville and Austin, they coordinate these STEM events. Their science festival to occur right about the same time as the UT girl STEM event. Around that whole, they make February a month of it.
There's a bunch of schools, we've done several in other school districts around this time too, then it's a
Yearly thing, right?
yeah.
Well, and then that week it was going to be the Texas Science Festival here on campus and probably elsewhere. The week of the Girls STEM Day.
And then the next actual event we have is on the 22nd, February 22nd, that's UT STEM Girl Day. I've gotten a few responses, 6 or 7 responses from volunteers volunteering. We'll still need more. I'm sending out another volunteer request on Monday with all the links for the safety video that every volunteer is required to use. There's also a lot of good links there, helpful information how to get in and out of there easy. If you come early, it should be fairly easy to get in and out. If you bring the telescope, there's an unloading area, so all that, I'll document all that in the email I'll send out Monday. As far as outreach goes, that's about it.
Do you also have, you going to do anything with the preschool on the 21st?
That's the one you just sent, right?
Yeah. So
Did I emailed you?
yeah,
right?
you had a conversation with her, an email conversation, and she said, "We're glad to have you out." So I think she's expecting somebody.
Right.
Yeah.
Yeah, so that's that's just some business we haven't really fully scheduled or confirmed yet, but yeah, my plan is to do that, to get somebody out there. Where is it?
Dripping.
Dripping Springs.
Yep.
Dripping spot,
Yeah.
right? Nice.
So we had 300 people show up at Pflugerville,
Wow. That's awesome.
and
That's
I
more
showed
per Dallas.
showed the moon at 300x to all 300 of them.
Long night.
Did not move the scope. Well, did not find another target.
Wow, well, we had, about 250 visitors at Pinellas Falls State Park. That's where, if anybody doesn't know, that's where we have our permanent installation with telescopes, and Greg brought out the 24-inch. And there were other scopes. You had, yeah, you guys both were there, and you were there, and Uncle Ed was there, and yeah, anyway, the scene was great. It was a perfect night. It was beautiful, and I could see color on the Orion Nebula through our 24-inch. But then Tony, I could see color through your scope too, and it was awesome.
Yeah,
And-
one of the
and
best
yours-
pieces of rock I've ever seen through my telescope.
Yeah, it was a great night. So that's pretty awesome at 300.
Well, if we're gonna get that many people at Pflugerville, we're probably gonna try and need to coax more of us out there.
Yeah.
We could also take advantage of it a lot of the people are asking for help on learning how to use their telescopes and night sky stuff. It's closer than Pedernales. We might start suggesting they go over there and we kind of peel off a little group on the side to work with them. We had, there was a peeled off group there when we were there, which was ACC had,
ACC, right, astronomy
Oh.
club.
their astronomy club was there.
So. Yeah, and I had, I'd gone to the UT Astronomy Club and invited folks out, but I don't know if any of them actually made it to Pedernales anyway. Awesome, sounds good. And then yeah, outreach, and then reports from any of the members at large. Anybody, Greg, anything new last month? Somebody else get in front of this camera.
So as Terry already mentioned, tomorrow is our grand opening for Area 51.2, which is going to have three main functions. Number one, we'll be doing telescope build, repair, and maintenance sessions there. So anybody who has a scope or that needs some work on it, needs some modifications, needs any kind of work, you can learn how to do that there. We're also going to be migrating our book library to that location. And we'll also be migrating our telescope lending library to that location. So all of the loaner scopes will be checked out and returned to that location, which will make it a lot easier than having to chase either to Bad Wolf or to Pedernales. I think our official opening time is 10 o'clock tomorrow morning. We'll be there till 4 in the afternoon, and we'll have pizza and sodas at lunchtime. Let's see.
Do we have books out and displayed now for the library?
We don't.
I intend to be putting some out tomorrow.
Oh, you
Okay,
will
so
be, okay.
we,
A couple
We've
of
got
Yeah,
some
you
there,
brought
we have
some, but
there,
You
and I
got,
have another box in my car,
okay,
and I'll have to have somebody get somebody to help me move it in, but yeah, I'm gonna start organizing the library tomorrow.
okay.
several of us are planning on being there at 8. That's when Jeff
Yeah.
is gonna.
Yeah, I don't know if I'll be there that early, but I will. try to get there early.
We do have the silver roll around wrap from Pedernales. It's there now.
Okay. That's what I was-
The other thing is that we just last weekend picked up another donor telescope, two more donor telescopes actually. Another one of them is another 24-inch Newtonian, Dobsonian. Its mirror is going to need to be recoded, and once that's done, or probably while that's being done, I think we're also going to be looking at adding a tracking system to it, because right now it doesn't have one at all. But once that's done, we're going to need some more volunteers to handle big scopes. So right now, Terry and myself are the only ones that have any training on the 24-inch Spica eyes that's out at Pedernales. So unless one of us are out there, that scope just stays in the shed. We'd like to be able to start training some other people on these big scopes, so we can hopefully bring more than one out at a time. And we may even end up taking one of them on the road with us to Pflugerville or some of these other star parties. But we need to start looking, we need to start gathering some volunteers to learn how to handle these big scopes, other than just bringing your own scope to star parties. We need to get people
Learn
trained
how
on
to
these.
get them out and get them set up. That's the
Yep.
big part. Yeah,
Yeah.
I can run it, but I don't know about.
Well, I'm working on a project to make getting the Spica eyes easier to get in and out the falling star. But I mean, it's really easy getting out. Gravity helps a lot. Getting it back in is the challenge. But hopefully I've extended the gravel pathway up to the end. I've extended the gravel pathway up to the end of the end of Falling Star, and we'll be building that up so that it's more or less even with the platform inside. So it's not, you're not gonna be pushing a 300-pound telescope up a 1 foot, 1 foot rise ramp, which is what we're doing right now.
So that's why it's easy to get out. You just open the
Oh, yeah,
door
yeah.
and push.
Like I said,
Roll it out.
gravity does all the work on that one. So anyway, though, we need to start looking for volunteers who can learn how to use those skills.
Our speaker is up there, by the way.
Oh, awesome. Okay.
And I think it's small enough.
Okay. Doctor, we're not sure. Is it Molyneux?
Molyneux, yeah.
Molyneux.
Joyce.
Joyce was right. She said, awesome. We are just wrapping up our business meeting here. And what was next on our agenda?
You have Dawn for Alcor.
Okay. Is Dawn on?
Yeah,
Yes, there she is. Okay.
I am on, and I will be brief, especially because I don't have much of a voice left. Few things to let folks know about. If you have been waiting for your reflector, it is actually going to be electronic this month. It looks like the Astronomical League is in the middle of shifting printing companies. So it will be published this month digital only, and your June issue will be a paper version mailed out. So just know that you need to go to the Astronomical League website, astroleague.org, to read this reflector for this month. Also, the designated days for Astronomy Day within Astronomical League this year are May 12th and September 27th. And then on March 7th, there'll be a live stream with Bob King taking a closer look at the night sky. That will be viewable live streamed on explorescientific.com site and also on Astronomical League's Facebook site. If anybody is looking forward to the Texas Star Party, those dates have been published as well on April 20th through the 27th out at Prude Ranch in Fort Davis. Also, don't forget, the AstroCon is going to be in Bryce Canyon National Park this year, June 25th through the 28th. So register and reserve your accommodations as soon as possible. Other than that, I have actually been working with the folks at NASA and JPL who are putting on a NASA house at the Central Austin Public Library coming up the first weekend of South by Southwest. And I'll be sending out, now that we've secured a location, sending out information about the Star Party we're co-hosting with them on March 8th for anybody who is interested. And if there are any folks that want to wander out to Lampasas on March 1st,
Oops, I just muted Dawn.
Hey, Dawn, you accidentally got muted. I think she has to unmute. Sorry, Dawn.
Dawn, I accidentally muted you. Sorry.
that's okay. It just took me a second to get the button. The Lampasas County Friends of the
So
Night
you're
Sky
talking about
host-
Lampasas.
Yes, they're hosting their Night Sky event again this year, and it will be on March 1st. And I will send out all that information now that we have all the details. And that's all I have.
Nice. Will they be needing volunteers at the public library downtown? That's an awesome place.
I will also include in the email all of the details about the NASA House events. They are going to be taking place at the library all day Saturday and all day Sunday on the 8th and 9th, and they're open to the public. No wristband is required.
Even better. Very nice. Awesome.
Can I
Thanks,
just
Dawn.
take this opportunity? Can I take this
Whatever.
opportunity to congratulate Dawn on becoming a solar system ambassador of NASA? Very
Oh, thank you.
There you go. Yeah.
really great. We good honor and very, very deserving honor, Dawn.
Thank you, Rajesh. I appreciate that.
Good job. She just found people to say nice things about her. Very nice. Thank you, Dawn, and whatever you're suffering from, you could have come here and shared it with everyone. but- Yeah. Fine, keep it to yourself.
Maybe next time.
Yeah, that sounds good. And then
You have a couple of things left. You've got Susie with Dark Sky and then any old or new business.
okay, and I think Susie's not on. She's celebrating her birthday and Valentine's Day in Cabo. I'm assuming she doesn't mean Bob's.
I don't think so.
Yeah. Awesome. Okay. And then just for business, I threw on the area 512, 512, whatever. And so Greg already talked about that. And then I just want to remind folks, we do need a nominating committee pretty quick, just 3 people to basically wrangle some new volunteers from our group who are willing to serve on our committee, our executive committee. That sounds so fancy. It's just running, we're running, you know, everything behind the scenes, but anybody can join and it's, yeah. I think for our next president should have a spouse and maybe be retired, but you know, so anyway, I think that's pretty much it. And Dr. Molyneux, normally we have quite a few more people. The audience here is starting to fill up and slowly but surely online, but we have the unfortunate timing here, it being Valentine's Day, and then the weather's, well, you're just south of us in San Antonio, so you know the weather is pretty crappy today.
Yep, not great today.
And we do record these, of course. I guess you told her about that, right? It's okay. We record these, and so folks, you know, kind of rely on being able to see them later. So that's where we get most of the people. So we're very excited to have you. In fact, I'm going to bring Joyce up now, who's going to introduce you. So thanks, everybody.
Okay, Terry, if you go ahead and I guess make her a co-host so she can share her screen.
Yep.
Take care of that.
Pippa, you can share your screen anytime.
Okay, great. Thank you. Yes.
Okay. Dr. Pippa Molyneux, I think I'm saying it right.
Yeah.
Planetary scientist at the Southwest Research Institute in San Antonio. She grew up in the UK, obtaining her PhD in physics, space instrumentation from the University of Leicester. Is that the way to pronounce that?
Yeah, that's correct.
Okay. In 2012, before moving to the US in 2016, her research focuses on ultraviolet spectroscopy of icy moons to understand the compositions of their surfaces and atmosphere, as well as the design and development of ultraviolet instrumentation for future planetary missions. She helped build and test the ultraviolet spectrograph on the JUICE mission and its sister instrument on Europa Clipper, and is looking forward to seeing what new discoveries these missions will uncover as they explore Jupiter's icy moons in the 2030s. So, Pippa, it's all yours.
Great, thank you. Thanks for inviting me to talk today. Please let me know if you have any trouble seeing my slides or anything. Let's get started. So I'm going to talk about some recent and upcoming opportunities that we've had to explore some of Jupiter's moons in the ultraviolet. So I'm going to talk about Jupiter's Galilean satellites. I'm sure you're all familiar with the Galilean satellites, but just as a reminder, the furthest one from Jupiter is Callisto, and then moving inwards, we come to Ganymede, then Europa, and then Io. And I'm really going to talk mostly about the 3 icy satellites, so from Europa outwards. So when Galileo first was observing these moons, they were just pricks of light, as shown in the diagram here. But the Galileo spacecraft, a few hundred years later, is where we got kind of the most comprehensive and detailed look at these moons to date. I'm not going to talk a lot about the Galileo mission, but I just wanted to kind of mention a few of the major discoveries at each of the moons, which kind of highlights why they're interesting and why we want to explore them more in the future. So at Callisto, the Galileo NIMS instrument, which is an infrared spectrometer, discovered a CO2 atmosphere. The atmosphere is kind of patchy, it's not global, and we don't fully understand what's causing it, why it's only in these localized patches yet. And on the right here, I'm showing the very highly cratered and old surface, mostly just so you can see the contrast as we move to Ganymede and Europa, where they have younger surfaces. So at Ganymede, the big discovery by Galileo really was the intrinsic, internally generated magnetic field. this is the only moon that we know of that has this intrinsic permanent magnetic field. And as you'll see later, and you may already know, this kind of field it leads to auroral ovals around Ganymede's north and south poles, similar to the northern lights on the Earth. And as you can see, again, here's a surface picture. It's a little bit icier and younger than Callisto's. Apparently, if you know geology and geography, this kind of shaped feature up here is kind of indicative of past activity. So potentially some kind of cryovolcanism has occurred there in the past. So at one point, at least, it was an active world. Maybe not so much anymore. But speaking of active locations, potentially, here's some images of a region called Connemara Chaos on Europa. So this kind of surface region where we're seeing all these kind of different features that are not like matching up with nearby regions. Everything is kind of going in these random directions. This is indicative of a surface that's kind of melted, pieces have moved around and refrozen. So at some point in the not too distant past, there was activity going on at Europa. And the other thing that Galileo observed there was that there was an induced magnetic field. So not as strong as the magnetic field that it detected at Ganymede, but the Galileo magnetometer saw these kind of fluctuations in the magnetic field near Europa, which indicate that there's a conductive subsurface liquid ocean. And so Europa in particular is like a huge target of interest for planetary scientists because of this young surface, this evidence of recent-ish activity and possibly ongoing activity, and this liquid ocean. So activity implies energy, ocean, there's liquid water. So these are some of the really key ingredients for a habitable environment. And so that was kind of one of the big reasons that we want to go back to these icy moons. And we will. So here's a schematic from the European Space Agency showing all the previous exploration of Jupiter. There's been a lot of missions that have flown past Jupiter on their way to the outer solar system. Galileo so far, well, not so far. Galileo was the only orbiter until Juno arrived at Jupiter in 2016. And then Juno is still active there. Europa Clipper is on its way, as is JUICE. And so these are the three missions that I'm going to focus most of my time on today. So the three missions, although they'll all be orbiting Jupiter at some point, or already are, they have kind of different science goals, different primary targets for their missions. So Juno is very much focused on Jupiter itself. It's in a polar orbit. It goes very close to Jupiter, and it's really interested in understanding what is going on inside the planet and how is its magnetic field being generated. On the other kind of other side of this slide, Europa Clipper similarly has one very focused target, in this case Europa, and it's very targeted on exploring that question of habitability, understanding is Europa really a habitable environment, and looking for potential landing sites for a future lander that could help us to understand if it is currently habitable. And then in the middle, we have JUICE, which is more of a broad mission. It does have a focus on Ganymede towards the end of the mission, but it will aim to explore the full Jupiter system. So its targets are all three icy moons and Jupiter itself. And also it will try to look at some of Jupiter's irregular satellites and Io as well. So really kind of trying to understand how the whole system was formed and evolved and interacts now. So I'm going to talk through each of these missions in turn, but they have one thing in common, as well as both all being at Jupiter. They all carry an ultraviolet spectrograph built here in San Antonio at the Southwest Research Institute. So SWIRI has a family of planetary ultraviolet spectrographs that goes back to the ALICE spectrograph on the Rosetta mission, which launched in 2004. And our latest version of this was the one on Europa Clipper, launched in 2024. So over 20 years of flight with these instruments now. And these drawings show that, the instruments are slightly different shapes, but they're ultimately the same. The optical design is the same. They work the same way. The slight differences are mostly just due to the kind of very specific targets that they're operating at. So for example, this one LRO LAMP is the Lunar Reconnaissance Orbiter Lyman Alpha Mapping Project. So it's at our Earth's moon, and because there's a lot of sunshine nearby the Earth compared to some of these outer planet missions, then it has this big baffle. So that's kind of the reason for some of the slight design changes here. Juno UVS has a scan mirror because Juno is a spinning spacecraft, so that allows us to have some more control over where the instrument is pointed. Whereas JUICE UVS and Europa UVS, they're on missions that are not spinning, they're 3-axis stabilized, so they don't need a scan mirror. So it's just kind of small design differences like that, but they all work in the same way. And that way is kind of shown here. So if we look at the top-down view that shows where all the kind of different elements of the instrument are, usually we'll be observing something through this main aperture, and the light's coming in, it gets reflected by this mirror, focused through a slit, which kind of defines our field of view, and then onto a reflective grating. And then the grating reflects different wavelengths of ultraviolet light to different positions on this detector. So at the detector, we get a 2D spectral spatial image like this. And this is showing a simulated image of Europa. And we see lines of emissions from specific gases. So Europa has a water vapor and oxygen atmosphere. So we see emission lines of oxygen, and we see hydrogen as well. Some of that is also reflected sunlight because the sun is also bright at this hydrogen line. And then as we move to the longer wavelengths, we see more and more reflected sunlight because the sun is just getting brighter at those longer wavelengths. So that's kind of how the instrument works. But why do we even want it to work? Why do we care about the UV? So a big motivation for developing these instruments was to look at atmospheres of comets, of planets, of moons. And so a lot of common gases like oxygen, hydrogen, nitrogen, all sorts, they emit light in the ultraviolet. So here are some examples of some icy moon observations using Hubble. So on the left, we have observations of Ganymede's aurora. As I mentioned, it has these auroral ovals. These are looking at an oxygen emission in the UV. And similarly at Europa, we see some emissions. The bottom two images are, again, oxygen emissions, and the top one is a hydrogen emission line. And these kind of observations were taken as evidence of maybe some water plumes emitting from Europa's South Pole. So another reason that we want to go there and explore. And as well as emitting light in the UV, some atmospheric gases that are common also absorb UV light. And we can make use of that as well. So for example, water vapor absorbs UV light. This is an image of Europa. Here's the dark thing in the middle, and it's in front of Jupiter. And you can see, hopefully, if your screen is good enough, you can see some kind of dark regions just extending outwards from Europa on this kind of bottom corner. And again, this is potential evidence of water vapor being kind of localized, like in a plume coming out of the moon. And this is the kind of thing that we'll search for with our UVS instruments when we are near to Europa. And as well as looking at the atmospheres, the UV is also useful for looking at surface emissions, surface reflectance, sorry. And one feature that's particularly interesting at the icy moons is a UV water ice change in reflectance. It's an absorption edge, we call it. So at around 165 nanometers, water ice goes from being very dark at shorter wavelengths to being very bright at longer wavelengths. And this was seen at Saturn's moons using the Cassini UVIS instrument. And it's also very clear in lab measurements of ice, and these are models and data from the lab. And these are on different scales, so I don't know if you can see this well, but this is the UV through the visible, whereas this is just the UV. So that's why these features look like they're in slightly different positions, but they're all at 165 nanometers. And so one of the things that LRO LAMP, which I mentioned, is one of our lunar UVSs. One of the things they do with that is they look at ratio images. So they look at how much light is reflected in this spectral region, which should be bright if there's ice there, to how much light is reflected a wavelength shorter than this absorption edge. So the larger the ratio, the more likely it is that ice is present, basically. So this is a map of some South Pole craters on the moon. And some of them have these kind of enhanced ratios where we think there may be water ice. But one thing that's kind of interesting about this is that although we know that Jupiter's icy moons have a lot of water ice, they don't really have this same sudden increase in the UV that we see at Saturn's moons. They do gradually increase in brightness, but even at the end of this this plot, even the brightest part of Ganymede that we're looking at here in this Hubble spectrum is reflecting about 10% of the sunlight, whereas this Enceladus one is already up to 40-50%. It gets a lot brighter. And so we think what might be happening is that the ice is less pure at Jupiter's icy moons. So it could be because of the radiation environment. So there's a lot of charged particles trapped within Jupiter's magnetic field and magnetosphere that are being kind of slammed into the surfaces of the moons, and they might lead to chemical changes and impurities that absorb UV light. And so we don't have very good spatially resolved measurements of this effect at Jupiter's moons yet. It's the only instrument that's sensitive enough to do this kind of study with Hubble is not an imaging spectrograph. It's we just get kind of integrated spectra, disk integrated, so we can just see like one hemisphere of the moon at a time. So that's something that we will hope to explore more with JUICE and Europa Clipper, and something that we actually started to do a little bit with some Juno data, which I will talk about next. So Juno launched in 2011, and it went into orbit around Jupiter in July 2016. It initially went into a 53.4-day orbit, and the plan was to have another burn, which would shorten the orbit to 14 days. But there was a bit of a glitch in the spacecraft. They noticed some issues with helium valves, and so they never went into that shorter orbit, which worked out quite nicely in a way, because it meant that as the kind of trajectory of the mission evolved, then towards the end of the mission, it started to bring the spacecraft close to the Galilean satellites. And so NASA and the PI Institute and everyone in charge of the mission leadership, applied to NASA to get permission to run an extended mission. And that's what we've been doing the past few years, which has allowed them to study some of these moons. I'm going to talk about some of the Juno observations of Ganymede in a minute. So specifically the Juno UVS observations. So UVS did also observe Europa and Io, but the best data we have came from the Ganymede flyby. And that's the one that I was most involved in. So that's what I'm going to talk about. So this kind of gives an overview of that Juno UVS, or Juno encounter with Ganymede. I'd say we call it the PJ34 encounter because it was on the 34th perijove pass of Jupiter. Yeah, just prior to that perijove, I believe. So this happened in June 2021. We got as close as just over 1,000 kilometers. And here's kind of an overview image just summarizing what the UV saw, what we saw with UVS. So anything green that you see, like these stripes over here, these are auroral and atmospheric emissions. And then on the day side of Ganymede, so between the two lines that show the terminators here, you also see these red regions. This is reflected sunlight. And yeah, we're just showing a Ganymede, Voyager, and Galileo map underneath. So you see that the data is in these kind of stripes. I already mentioned Juno is spinning. It spins every 30 seconds. So at each spin, we get like a stripe of data, and it moves across the surface. We use the scan mirror that I mentioned as well to kind of target different parts of the surface as we move. So we have some gaps, but we have generally kind of good coverage from the night side over here going on to the day side. So if we start by thinking about the surface reflectance, I've kind of already mentioned some of this, but we see this gradual increase in reflectance on Ganymede in the disk integrated data. And even on the darkest of Saturn's moons like Phoebe, which is 2% reflectance at this long edge, we still see this like step up, which we just don't see on Ganymede. But we haven't been able to previously map this part of the UV because Hubble is just not sensitive enough with its imaging instruments to to give us this image. The closest thing we had was, sorry, this is blurry, but this is a map of the 121.6 nanometer reflectance. This is a bright solar hydrogen line that's being reflected, but it's really not a great map. And so this is kind of the improvement that we got from the Juno data. So as I mentioned before with the ratio that we did at the moon, we did a similar kind of ratio here. So we're plotting the ratio of this region in the red where water ice should be bright to this region in the blue where water ice should be dark. So everywhere we see these kind of red ratios at the top of this color scale, that's where we're most likely to detect some kind of feature of water ice. And you can see that it maps fairly nicely with the visible map. So for example, around this feature, there's, you definitely see that transition from the red high ratios to the low ratios within this dark region. But it is quite noisy. And that a lot of that is just due to the fact that we're spinning very fast. So as I mentioned, it's a 30-second spin for a 360-degree spin of the spacecraft. So every kind of pixel along our swath of data here is only getting something like 17 milliseconds of exposure time. So we're really not seeing that many photons, so it is noisy. So to extract kind of representative spectra, then we needed to bin over larger regions so that we could improve that noise, the signal to noise level a bit there. So it chose kind of 3 regions with different surface characteristics. So these high latitudes shown by this blue box, this is a region where we expect to see a lot of water ice. We know from observations in the visible and infrared that there's a lot of water ice there. So we were searching for the UV feature in that region. And then in this green box, this is showing Tross crater, which is a very bright young crater, one of the youngest craters on Ganymede. So again, in the infrared and visible, there's a lot of evidence for a lot of water ice there. So it's a good place to look for the UV feature. And then we also looked at the low latitudes for comparison. So this region is dark in the visible, and there's less water ice there. We know that from other wavelengths. But again, when we extract the reflectance spectra from these regions, we still don't really see that step up in reflectance right around 165 nanometers. But there are kind of subtle differences between each of these regions. So for example, the high latitudes do become brighter than the low latitudes right around 165 nanometers, just not by a dramatic amount. And then Tross crater was kind of interesting because it was kind of even darker than the low latitudes until about 190 nanometers, where it kind of shoots up in reflectance. But these differences are very subtle. So to try and emphasize some of them a little bit more, we can take the ratio of these lines. So if we ratio, for example, this blue line to this orange line, the high latitudes to the low latitudes, then we would expect any kind of spectral differences, so any differences in the composition, to really kind of jump out. And when we do that, we did actually finally see this step up in reflectance. So I know I've mentioned 165 nanometers is pushed a little bit to longer wavelengths, but this is actually something that we expect from models if the grains that the ice is made of are larger than they are on Saturn's moons. This feature kind of shifts around a bit, but not by more than kind of 5 or 8 nanometers, maybe at the most. So this is kind of as we expected. There's also this extra material absorbing at the long wavelengths that we thought might be the beginning of a known ozone absorption feature. After looking more into that with some Hubble data, we now think it's something else, but we're still kind of working on figuring out exactly what this is. But the main thing is that we saw this water ice feature in that ratio of the high latitudes to the low latitudes. Whereas when we ratioed the Tross crater region to the low latitudes, it looked very different. So there's no way to scale this water ice model to make it fit with what we're seeing in this Tross crater region. It just remains dark. So what we think might be going on is, as I mentioned, if there are impurities trapped in the ice, either because the radiation is modifying the chemicals, or maybe there's something to do with just nearby material is just getting caught up in the ice as it's being processed, then that can actually flatten this spectrum quite easily, we found. So even with a very small amount of a contaminating material, like less than 1%, we were able to model a very dramatic change in the brightness of this spectrum. So the fact that we're seeing TROS remain darker than those high latitudes, that suggests that either the ice grain size is larger, because for a given concentration of contaminant, if you make the ice grain larger, then it absorbs more. It darkens the spectrum more because the light has to travel kind of further through this material to get to the other side of the ice grain and be reflected. So the ice grains may be larger at TROS, or they contain higher concentrations of impurities, or they contain different impurities that are more absorbing in this UV region. We can't really distinguish between those effects until we go there and measure them in more detail. But okay, if there is a contaminant, then how do we know what it is? Well, we tried to compare the shape of the spectrum that we were getting to a bunch of spectral libraries and measured materials in the UV. And the best fit that we found was for ammonia, which covers this purple line, and it really does a good job of fitting most of this region. But that was a surprise because ammonia ice is not really expected to remain stable at the temperatures of Ganymede's day side, not for very long. So if it is ammonia, then, you know, when did it get there? How is it stable? But I will say that the infrared instrument on Juno, they also observed some ammonia salts on Ganymede. So it may be that it's not pure ammonia, but it may be like some kind of ammonia related material that has a similar spectral shape in the UV, and maybe we just don't have a measurement of that material yet. But to really understand what's going on, then we need to know if this is kind of a consistent signature, if it was just kind of a weird one-off, if it's happening in other craters, if it's unique to TROS. We need more information, so we need to go back and explore more. And then the other thing we did was we looked at Ganymede's aurora. So from the Earth, we did have existing images of Ganymede's aurora. We have looked at it multiple times with the Hubble Space Telescope, but we were clearly able to see, resolve it in much finer detail when we looked with Juno UVS. So we were able to kind of constrain the width of the auroral ovals, and we were we compared the shape of the auroral oval to the expected location of the auroral oval. So these kind of lines that I'm following now with my pointer, these are modeled expected positions of Ganymede's open closed magnetic field line boundary. So if you kind of picture a bar magnet like this is kind of this location here between where the field lines are closing on both sides to the magnet and when they're more open to a further distance. And that's the location where we see the auroral ovals on Earth. And so that's kind of where we expected to see them on Ganymede. We kind of knew they were there. And the model fits really nicely in a lot of these locations, but there's this slight kind of divergence in the north here. So this kind of suggests that, again, we don't fully understand the exact configuration of the magnetic field. And again, we need more measurements. Another thing that we have done before with Hubble is we've looked at how these these locations of the auroral ovals change as Jupiter rotates. So Jupiter has a 10-hour period rotation. Its magnetic axis is offset from its rotation axis. So that means that its magnetic field is tilted relative to Ganymede, and that tilt changes over a 10-hour period. So it goes from being kind of like this to pointing up towards the north. And that causes a motion of this like open closed field line boundary at Ganymede. And so this study by Sauer et al., they showed that if there's a subsurface ocean at Ganymede, which had been suggested, then there would be an induced magnetic field within that conductive ocean, which would act to reduce some of that rocking motion and that movement of the aurora over Jupiter's rotation. And so they showed from Hubble observations that, yes, the auroral oval rock, less than we would expect if this was a solid body. So there is most likely a conductive subsurface ocean. And we will clearly, with Juno, we've had one measurement with Juno. This is similar to what we'll see with JUICE and UVS and Europa UVS, and we'll be able to kind of measure that rocking in much more detail and see what we can constrain about Jupiter's, Ganymede's interior from that. So there's lots we can do with this kind of data. Another thing that we did for the first time was we were able to look at more of this kind of latitudinal extent because we had this kind of spatial resolution that we don't have with Hubble. And what we saw was that these emissions are kind of cut off very sharply at these kind of outer edges, but they decrease kind of more gradually towards the equator. And we don't know why that is happening yet. We don't know if it always happens like that, or if this is just during this particular flyby, the magnetic field was in a particular configuration that made us see that. So there's lots that we can learn by going back to Ganymede and doing this kind of over time, seeing how this interaction changes, what the aurora looks like at different magnetic field locations and all of that kind of thing. Yeah, so as I've mentioned here, this is the stuff that we'll be able to do with JUICE. And a key thing as well is that we will have simultaneous UV observations and also in situ measurements, so direct measurements of the particles that are responsible for exciting these auroral emissions. So this is a really nice preview for our future exploration of these moons. As I said, Juno is spinning, so our exposure times are very low. When we get here with JUICE, we'll be able to stare, we'll be able to kind of point wherever we like and look at these emissions for much longer. And really kind of understand at good signal to noise what's going on. And we'll be able to do this repeatedly and understand how these variations are occurring over different timescales. So speaking of JUICE and Europa Clipper, these are the missions that will help us to enhance this kind of study and to repeat what Juno has done, but do it in so much more detail and over a long time. So JUICE launched in 2023. It will reach Jupiter in 2031, and then it will do a tour of the Jupiter system where it will do multiple flybys of each of the icy Galilean satellites. So 2 Europa flybys, 21 Callisto flybys, and 12 Ganymede flybys. And the lowest ones are going to be on Callisto. It gets down to about 200 kilometers there. At Europa and Ganymede, the flybys are around 400 kilometers or more. But then at the end of that tour, JUICE will go into an orbit around Ganymede. And it will spend some time in a 500 kilometer circular orbit, but then it will go down to 200 kilometers. So it will get very close to Ganymede as well. Meanwhile, Europa
JUICE
Clipper
doesn't have any interest in Io?
It will look from a distance, but it won't get close to Io. The radiation environment is just very difficult. Even around Europa, it's quite difficult. That's why there's only 2 Europa flybys. But yeah, Io is difficult to explore close up, but we will be observing it definitely from a distance. And yeah, meanwhile, Europa Clipper, which reaches Jupiter in 2030, so slightly earlier than JUICE, despite launching a year later. As I said, it's very focused on Europa science, and there will be 49 Europa flybys, and they get as low as 25 kilometers. So not all of them are that low, but a lot of them are within that 25 to 100 kilometer altitude range. So they get very close to the surface, and they'll get very high resolution, detailed observations of that moon. So I imagine this is quite small on your screen, but JUICE carries 10 instruments, and I'll just talk about kind of the different groups of them rather than expecting you to read all of this information. So there are 4 remote sensing instruments, including the UV spectrograph. So we have an optical imaging system which has various filters to look at different emissions and different surface reflectance bands. There's a visible and infrared imaging spectrometer, the UVS that we've already talked about, and there's also this sub-millimeter wave instrument, which is pretty unique to JUICE. It's quite new. It looks at kind of vibrations and rotations and things within molecules in atmospheres. So it can get very detailed information like isotope ratios in the water vapor, which can tell you where that water vapor came from. So whether that water was, intrinsic to the moons when they developed, or if it's been delivered from somewhere else, and that kind of thing. And then as well as the remote sensing observations and instruments, we have some geophysical instruments. So there's a radar sounder, a laser altimeter, and a radio science experiment, which will tell us about the surface topography and kind of the subsurface, near surface structure. And then we have some in situ measurements, in situ experiments. So they measure the magnetic fields and the particles in Jupiter's magnetosphere and waves and that kind of thing. On Europa Clipper, there's also kind of a wide range of instruments. Again, there's several remote sensing ones, including UVS, ICE-WAC and ICE-NAC. They're the wide angle and narrow angle camera. There's a mid-infrared spectrograph. And eThemis is a thermal imager. So that's something that JUICE doesn't have. And again, some in situ and geophysics instruments as well. So a direct comparison is kind of more useful in this table. So you can see that a lot of the time, JUICE and Europa have very complementary instrumentation. UVS is the only instrument that's completely identical, although I think Rime and Reason are also very similar. But so these have similar capabilities, but some of them are kind of more capable on one than the other. For example, JUICE is really very interested in understanding Ganymede's magnetosphere, so it has more kind of capable magnetometer and plasma instrument suite than the equivalent on Europa Clipper. But then again, Europa Clipper has extra things that we don't on JUICE, like the thermal imager and this dust detector. And again, their trajectories similarly are kind of complementary, but not identical. So we will get different information from the two missions, even though they're exploring the system at the same time. So Clipper will be mostly in this equatorial plane. So we'll see kind of mostly the near equator parts of the moons, whereas JUICE has this period in the middle of its tour of the Jupiter system where it goes to quite high inclinations. And that will let us look at Jupiter's aurora. And it also, I think it is useful for, it helps to kind of change the trajectory and get it into the right orientation to go into orbit around Ganymede. So that's the reason for that. So JUICE, as I've mentioned, it has quite broad science themes. So the first theme is to explore the habitable zone of these three icy satellites, particularly in characterizing Ganymede as a planetary object and possible habitat. So although we've kind of talked about Europa being the habitable environment, and as I showed in that Galileo image, there's potential evidence for previous activity on Ganymede. We do know that there's subsurface ocean there from looking at the auroral rotations and rocking motions. So it's possible that Ganymede is also habitable. And then we want to explore Europa's recently active zones, all these locations where we think there may be evidence of these water plumes emanating from the subsurface. And Callisto is also very important. Callisto kind of gets overlooked a little bit sometimes, but it has this very old surface. It's less evolved, maybe, if that's the right word, than the other two. So it kind of gives us a window into the past of the Jovian system. So some of the materials there have been less processed and less, they're not in this active zone that Europa and Ganymede perhaps are. So that can tell us more about how these moons formed. And by comparing the three and Io as well, this tells us about the history of the whole system. And then speaking of the whole system, the second theme of the JUICE mission is to explore the Jupiter system as an archetype of gas giants. And so we'll characterize the Jovian atmosphere, we'll characterize the Jovian magnetosphere, and we will also look at the satellites and rings, which, you don't often think of Jupiter's rings, but they are there. I don't know if we'll be able to see them in the UV. We're going to try, but they're probably going to be too faint for us to see. But some instruments like the camera and the the infrared instrument as well, I think are going to try and observe them. And so specifically JUICE UVS, we have kind of science objectives that come under these two themes. So our first objective is to explore the atmospheres, plasma interactions, and surfaces of the satellites. So this will be very similar to some of the work we did with the Juno flyby data, again, mapping the auroral and airglow emissions of various atmospheric species, and also mapping surface volatiles, particularly water ice, but looking for things like CO2 and ammonia. And another thing we can do that we can't do with Juno because it's spinning is that we can do these stellar occultation observations. So we look at starlight as a star is either passing behind a moon or in this case, emerging from behind of it. We look at how that starlight is absorbed by atmospheric gases, and that tells us about the composition and distribution of the atmospheres of these moons. And we can also do this kind of absorption study with Jupiter transits, like that Hubble image I showed of Europa in front of Jupiter. Then at Jupiter itself, we will look at the atmosphere, the upper atmosphere, and we'll be studying dynamics, chemistry, and vertical structure. So again, we'll be doing these reflected sunlight maps across the full disk. In this case, we'll be looking at absorption by hydrocarbons, probably seeing how they are distributed throughout Jupiter's atmosphere and how they vary over time. We'll be able to map the aurora, and we'll look at the morphology and variability. We won't do it as well as Juno does. So we'd never get as close to the poles as Juno gets. So we won't have quite this resolution as shown on the left here, but on the right, this is kind of a simulation of what we would want to see. And critically, when we're in orbit, we can see the night side of Jupiter. So you can get nice auroral images using Hubble, but you can never see the night side of the planet. So this gives us extra information as well. And again, we'll be doing stellar occultations, this time looking for different atmospheric gases, so more hydrocarbons. And then finally, Io, somebody mentioned Io. So we really are interested in understanding how Io's atmosphere is formed and interacting with the rest of the system. So we'll be looking again for auroral emissions. We'll also be looking at Io's neutral cloud. So this is neutral atoms and molecules that are released from Io's volcanoes and form this neutral cloud. And then as that material kind of collides and ionizes, then it forms into this plasma torus, which gets pulled along by Jupiter's magnetic field as it rotates. So yeah, it becomes this kind of donut-shaped region of plasma. And there are lots of emission lines of, sulfur ions, oxygen ions, have very strong emissions in the UV. So here's an example of images of the Io torus taken by the Cassini UVIS in that EUV channel. So this is kind of, again, wavelength is increasing towards the right. And you start to see in the middle here, so that the Io torus is kind of like vertically oriented here. And then Jupiter is right in the middle, and you start to see reflected sunlight from Jupiter at these longer wavelengths as the sun starts to get brighter. So in contrast, Europa is much more focused. Europa Clipper is much more focused on Europa, but it will do a very thorough job of characterizing kind of everything about Europa. So it's ice shell, ocean, surface, subsurface, its surface composition, its atmospheric composition, any ongoing activity, and it will also act as a kind of reconnaissance for possible future landing. So if it looks like it's habitable and it's worth exploring more, then where's the best and safest place for us to land in future? And so that means that, again, like the UVS science objectives for Europa Clipper will be a bit more targeted. They're similar to the JUICE ones, but they'll be more focused in that first category that I talked about of looking at the atmospheres and surfaces of the icy moons, and in this case, really focused on Europa. So that's kind of what we have to look forward to. And so where are the missions right now? JUICE, as I said, it launched in 2023. We've already done one gravity assist maneuver last summer, which is a lunar Earth flyby. And now JUICE is rapidly approaching Venus. So it's still in the inner solar system. There'll be a Venus flyby in August this year. We won't be able to observe Venus during that time. It's just going to be too hot. And because also Venus will be not on the same side of the sun as the Earth at that point, it's very difficult to get the data back, and it's just a risky thing to do when you can't communicate with the spacecraft very easily. So nobody will be observing during this flyby, but it's still a still exciting part of the mission and an important part of the mission. And then following that, it will continue to hang out in the inner solar system for a while. There are 2 more Earth flybys, and it'll finally start heading out to Jupiter in 2029, and again arrive there in 2031. Meanwhile, Clipper, which launched only last October, it's very close to Mars right now, 2 weeks out from its Mars gravity assist. So look out for news about that. I think there'll probably be some press releases. UVS will not be observing, but I think 2 instruments will be doing at least some calibration, and I'm sure there'll be some images and press releases coming out for that. And so Europa Clipper, because it launched on a bigger launch vehicle, it doesn't spend as much time doing gravity assist. So there's only one more, an Earth assist next year, and then it will be straight up to Jupiter. And that's why it arrives a little bit earlier. So we've talked about kind of the future and the present, and I thought I'd finish by just sharing a little bit about my experiences of putting these instruments together and working on these missions so far, because this job is kind of unique and not a lot of people get to experience it. So I joined SWRI in 2016. Both of Europa UVS and JUICE UVS were kind of already in process at that point, but they hadn't been built. They hadn't had all the optics installed. So I helped with that kind of optical installation and alignment and focusing tests. And then I helped with the ground calibration that we did before we delivered the instrument. So this is kind of showing the lab we use for the calibration. So we have a lamp, and it focuses, it sends light through this monochromator, which we can either use to select specific wavelengths, or we can leave it open to look at all wavelengths. And that goes into this 5-meter long beam line. And then the test chamber is right at the end. It's kind of hidden, but it's in this like clean cabin at the back. So the instrument at this point would have been in this chamber right at the back. And when we switch the lamp on, it glows. So the lamp is filled with gas. In this case, it's neon. You can tell from the color. And then there's a high voltage applied across it, which makes it glow. And then at the instrument, we see all of the different UV emission lines. So this is a neon spectrum that we measured during this calibration. This is the kind of spectral image we'd get at the instrument, and then we can kind of flatten it to get a spectrum. And this helps us to understand which pixels correspond to which wavelengths, because we know what wavelengths neon emits at, and like how good our resolution is, how good our focus is, because we look at how broad these lines are. And then we have the ability to kind of tip and rotate the instrument as well, so we can make sure that everything across the full field of view is acting as we like. So I helped out with that. You can probably kind of guess when this was during this period from the masks, but this was towards the end of this period, right before we delivered. So we delivered JUICE UVS in 2020, in February 2020, so just in time. And then Europa UVS was delivered in 2022. And following delivery, we would go to the spacecraft and do periodic tests, especially if the spacecraft had been moved or gone through some kind of environmental testing like vibration. We just want to check that the instrument is still acting as expected. So I wasn't able to help out with the JUICE tests for this. Again, it was pandemic time, so very limited on who could travel. But I did get to go and help with the Europa Clipper tests. So when the spacecraft was in the clean room at JPL, they had a live stream to YouTube. So somebody in San Antonio took this screenshot while we're in there. I think this is me here working on the instrument. And then our final test was at Kennedy Space Center just before launch, a few months before launch. So in each case, you see this kind of red structure. That's our ground support equipment. So we have a UV lamp attached here. It's a deuterium bulb. And then we have like vacuum pumps and gauges, because our detector has to be under vacuum to operate. So this is kind of just after we had got this lamp to work perfectly and we wanted to commemorate the occasion. And then this is the very last image after we'd taken the ground support equipment off, and we had inspected the instrument and we were saying goodbye to UVS. So this is very rewarding to be part of. Very few people get to touch the spacecraft, so that was a real honor, but it is quite tiring, very long days. And yeah, clean room suits are not the most comfortable. So the more fun part of the experience for me, the most fun part so far was the JUICE launch in French Guiana. So I was lucky enough to be able to travel down there for that. Really unique experience, seeing my first rocket launch as well, and seeing it from kind of the jungle rainforest. I don't know how well you can make out these images, but we saw sloths, we saw monkeys, and of course the launch itself was spectacular. Well, I thought it was spectacular. I had a friend who did outreach with some local kids. You can see it was a very cloudy day when we launched. So she would ask them, "Did you see the launch?" And they'd say, "Yeah, it wasn't a good one," but it was very good for me. And then 2 months after launch, I helped out with the commissioning of the instrument in the European Space Operations Center in Germany. So I know these images don't look very exciting, but this was kind of the key point. So at the top, there's a screen where not much is happening. And on the bottom, we turned on our instrument and suddenly we're getting all this data back. So that was very exciting. And as part of the the commissioning activities, we were able to do this roll. So the spacecraft rolled 360 degrees, and we kind of plotted this path across the sky and looked for all the UV stars. So this is a kind of zoom in inset here, is showing some of those UV bright stars. And then if you can make it out, there's a little diffuse emission down here. That's the Large Magellanic Cloud. And this was our very first image. This is again, just that hydrogen Lyman alpha line. It's everywhere. Hydrogen, this is very bright. So we're just looking at empty space basically, and we just see an image of our field of view and hydrogen emissions. So that was exciting. And then, as I mentioned, JUICE came back to Earth last summer. So here's an ESA time-lapse video. I should have put a link here, but it's on YouTube. And so we flew past the moon about, I think, 700-kilometer altitude was our closest approach. And then a day later, we flew past the Earth. So this kind of fast forwards a little bit, and then you'll start to see the Earth in a minute. We didn't get as close to the Earth. I think it was something like 6,000 or 7,000 kilometers, but we were able to observe the Earth and the moon. We did collect some spectra. It wasn't kind of in the best orientation for us to make a map or anything, but we did kind of get some filled field of view images, which we'll be able to use more for calibration. And then again, we did this kind of spacecraft spin where we're able to observe. So in this case, we weren't quite on the moon, on the Earth. This was a few days after the flyby, but we did see all this kind of extended emission around the Earth. So this is again that hydrogen emission. So this is hydrogen that's moving outwards into the Earth's geocorona, and it's scattering sunlight. And then I'm sure you recognize the Pleiades up here, and then some other UV bright stars at the bottom. And then, of course, the Europa Clipper launch was also last year, just as memorable as the JUICE launch, but for slightly different reasons. So we were right in the eye of Hurricane Milton. Some of us were already in Florida before Milton even became a storm, so we stuck it out. Some people kind of drove as far north as they could and then came back for the launch. Some people who hadn't traveled yet just came out later. So the launch was ultimately delayed by about 4 days. And the hurricane itself was only kind of category 1 by the time it passed over us. It wasn't too bad. But what we weren't expecting was a tornado to touch down right outside our hotel. So this is kind of a parking structure next door that was damaged by that. But finally, after that, the launch was on a beautiful day. We were closer to the launch than we were for the JUICE one. So that was really fun to see. But yeah, it was a sweltering day. So here's me and my husband kind of sheltering under the bleachers while we waited for the launch. Again, a really exciting opportunity, and yeah, real privilege to be able to work on these missions. So what's coming next? So we did the JUICE commissioning in Germany 2 months after launch. Similarly, we had to commission Europa UVS. NASA kind of split out the activities a little bit more for that. So we did start it, and then the second phase of the commissioning was happening in January, just when the LA fires broke out. So we had to pause that, and that will kind of be delayed until after this Mars flyby, which is the real priority for the mission at the moment. So the Mars flyby is coming up in 2 weeks. As I said, look out for kind of press releases and things about that. And then JUICE flyby in August, we won't be observing, but we will be kind of waiting to just get the news back from the mission that everything went as planned, which we expect it will. And meanwhile, you know, the spacecraft are off there kind of just waiting to do their thing, but we're doing a lot of activities on the ground. So we have regular activities, checkout activities for JUICE. About twice a year, we're able to turn the instrument on and just do a couple of basic tests and observations. So we often try and do those spins that I talked about where we observe some stars. That helps us to understand exactly where we're pointing, and it also kind of understands by comparing what we measure of the stars to kind of models or previous observations of those stars, helps us to understand kind of our instrument response at all these wavelengths. And we're also doing a lot of planning exercises. So JUICE right now, we're in the middle of an exercise where all the instrument teams are talking about one particular orbit. And so from a 22-day period, which includes a Callisto flyby and a Jupiter perijove. And we're all kind of arguing about who gets to observe when, and you know where we want to point. So just so we can get prepared for when we get there and we don't have time to argue, we need to know what we want to look at. So there's lots going on, lots for you all to look out for in the next few years as well as we get closer to these mission targets. So thank you so much for inviting me and for listening. If you're interested in learning more about JUICE in particular, there is a feature-length film documentary about the making of JUICE. So this QR code will take you there. You can just go to YouTube and search for the making of JUICE, the film, and I'm sure you'll find it very easily. Thanks.
This is time for questions. No. Oh, okay. Awesome. Yeah, we've got some questions online and I'm sure we've got some here. Terry, can you read the ones from online?
Yeah, we've got one from Varga here. You mentioned that JUICE will be looking at Jupiter's atmosphere as one of its goals. Will it be attempting to confirm the composition data that we got from Galileo, specifically water vapor levels?
So it will be looking at water vapor levels, yeah. So the amount of water vapor at Jupiter, it's not something I know a lot about, but I know that sometimes there's been kind of comet impacts that can enhance the amount of water that's present. So we are definitely interested in kind of understanding if that water vapor component is changing over time and trying to understand where it came from and how it evolves. Yeah. And then more generally, we're looking for, everything, confirming, yes, previous observations of what's been seen there, and also seeing, just having the opportunity to study the atmosphere over different time scales and day and night and over, the few years of the mission and seeing how things vary and change and what things don't vary.
Any questions?
So both the spacecraft, when they're doing the flybys, gravity assists, are they actually going to be using their instruments to observe the planets at that time?
So all the instruments would like to observe as much as possible. So for the lunar Earth flyby that I mentioned for JUICE, originally they didn't want anyone to observe because this was, the first gravity assist. It was kind of a critical maneuver, but all the instruments kind of pushed back and said, this is, first of all, it's really interesting for us for calibration reasons as well as for science reasons. And, if there's a way to do it safely, then, please do everything you can. So we were a little restricted in what times we could observe, but in the end, we were able to observe. But yeah, I think some instruments did also try and push for observing in the Venus one. That was a definite no, just because it's a very hot environment. And again, the data rate and the telemetry coming back is quite sparse, and we really need to focus on making sure the spacecraft itself is safe. But yeah, for future Earth flybys, I think we'll be able to observe with JUICE. For Europa Clipper, I'm not so sure about the status. I do know that a few instruments are doing some kind of calibration and checkout activities on Mars, but it's really kind of a matter of prioritizing who really needs it, right? So for example, in JUICE, one of the instruments, the RIME antenna, didn't deploy properly as it left Earth. Eventually it did, but it took about 3 weeks to kind of get it loose. And that meant that they weren't close enough to the Earth to do some of their kind of calibration that they needed to do to get started. So they were kind of given priority during the lunar Earth flyby, and they could, have the highest data volume and that kind of thing. So there's kind of prioritization like that. If we're limited, then the instrument that needs it the most to make sure that they're operating well and are going to do well in the Jupiter environment, they'll be given priority.
I just asked that because it seems like it was when Cassini did some gravity flybys of Earth on the way out to Saturn. They had some experiment there to basically prove that there was life on Earth.
Oh. Yeah, so there was actually a press release from one of the JUICE instruments that said, JUICE confirms presence of life on Earth. So we did kind of similar stuff. We looked at, the atmospheric gases and showed that we could detect, water vapor, ozone, things like that, that were kind of consistent with life.
Good to get that confirmation.
Yeah.
Well, I was, I'm very impressed that you're working with the folks who are doing Juno, who sent, I guess, the principal investigator and all of that. And so Juno's still going.
Mhm.
And did you say that it initially wasn't supposed to be gathering data from the moons?
Well, it's because of the change they had to make to the orbit. So originally it was going to go into this shorter orbit, which would have always been kind of closer to Jupiter. So it just probably the orbit wouldn't have evolved to be as close to Ganymede as it ended up being.
Wow, that's awesome. So what is it like working at Southwest Research Institute? That's
Yeah, there's so much going on. So yeah, it's cool. You get the opportunity to work on some really impressive missions. You know, we obviously have a great reputation for space science, and being able to be a part of that is definitely a privilege. It's yeah, sometimes you kind of need to step back a bit and think about what everyone else is doing, because you get kind of focused on your own work. But yeah, when you think about all the missions that are coming out of Murry and the instruments, then yeah, there's so much inspirational planetary science being done there, and not just planetary science as well. There's in our division, you know, there's people who work on heliospheric science, so looking at the Earth's magnetosphere and the sun and the interaction between the sun and the Earth, and also there's some astrophysicists as well. And then Murry as a whole, you know, they do all sorts of things from like what they say from deep space to deep sea, or maybe the other way around, but you know, all sorts of different activities going on. Anything to do with physics and engineering, you know, Murry has probably got something to do with it. So yeah, it's an interesting, definitely vibrant place to work.
amazing. Were there any other questions online? Is that
I think I would just see the one.
okay?
If somebody else had a question, go ahead and ask it again.
Yes, I had a question. Can you hear me?
Yeah.
Yes.
Oh, I was wondering, and thank you. That was a wonderful presentation. I'm very impressed. But I was curious about the UV instruments. Will they be looking at any sulfur-related compounds?
Yes. At IO particularly, we're sensitive to some sulfur emissions, so sulfur emission lines. And we also can see things SO2 we can see in absorption. So yeah, very relevant to our IO science. So particularly for JUICE UVS.
Oh, well, thank you. I'm curious if that is in any way related to biological activity.
So not at IO, it's very intense, but yeah, sulfur is a species that is you know, one of the key materials that is like implicated in life, I guess. So we will, yeah, we expect to see it at IO. We will be looking for it elsewhere as well. There's definitely sulfur species throughout the Jupiter magnetosphere, and some of that sulfur is kind of impinging on Europa, and it may interact with the ice and form, you know, different kinds of molecules, sulfur-related chemistry that, yeah, could be a key part of that habitability question. So yeah, definitely something that will be explored by us and by the other kind of spectral instruments as well, and the more of the direct measurements from the mass spectrometer, for example. They'll be looking for all sorts of things in the atmosphere of Europa. So yeah, maybe we'll see some kind of sulfur related things.
Yeah, well, can't wait till 2030, 31.
Yeah, you know.
Well, thank you.
Getting closer.
Is it taking so long for them to get out there because of all those planetary flybys and assists and all that?
So it's partly due to the size of the spacecraft, because they're heavy, they need a lot of acceleration. You can't just kind of directly shoot them out there with the amount of kind of thrust you get from a rocket. You need to kind of use that energy from the flybys to accelerate them. But it's also just due to the way that the planets are lined up. So, you know, famously, when the Voyagers launched, they were like a very good time for the planets were all kind of aligned, so you could kind of sling past one and onto the next. Whereas now they're sort of moving into worse positions. So in fact, JUICE was supposed to launch in 2020, and it would have taken, I think, 2 years less time to get to Jupiter if it had launched then. But because we had to wait 2 years, then it kind of extended that cruise time, because the planets just aren't lined up as easily for us to kind of sling past them and get out to Jupiter. So yeah, it's partly timing, partly, yeah, because these are big spacecraft that are heavy and take a long time to accelerate.
Amazing. Well, the news said that all the planets are in a row right now, so.
Yeah, from the Earth, but maybe not in the best locations for a spacecraft to encounter them all. But yeah, maybe if we had launched 2 years ago, we would be kind of slinging past them.
I'll make this cue shot. I don't recall if you mentioned, but what's the ultimate fate of both Juice and Clipper?
That's a good question. Yeah, so Juice will eventually slam into Ganymede. Europa Clipper, we're also hoping will slam into Ganymede, and we're hoping that we'll be able to do it when Juice is in orbit of Ganymede, and then we'll be able to look at the materials that are thrown out, and that will tell us more about Ganymede's composition. But I'm not sure if the end of mission plan is really set. I know that they absolutely do not want to impact Europa, so they were going to impact either Callisto or Ganymede, but I'm not sure if there's what the current idea is for Clipper. Juice, because it goes into orbit around Ganymede, it will just eventually crash into Ganymede.
So how seriously were the spacecraft sterilized before they were locked up, tied up and sent off?
Yeah, we did have very strict planetary protection procedures. So yeah, there was lots of kind of everything had to be baked out to make sure, everything is clean. Everything is only handled in the clean room. There are strict kind of procedures for when you go in the clean room, what you're wearing, and don't touch your face, clean your gloves. If you touch your face, replace your gloves, that kind of thing. So there's definitely been a lot of concern about that all the way, and we had regular inspections. So every time we would go and do a test of UVS on the spacecraft, then we would have a contamination control guy there who would help us look into the instrument, make sure there was no visible debris to start with, and then they were taking swabs and things, making sure that there's nothing unexpected on the spacecraft. So yeah, Europa Clipper in particular has to be very careful because Europa is classed as more potentially habitable than Ganymede. It's kind of one step up in the classification. But Juice was also, very carefully controlled, but we didn't have this quite strict testing quite as frequently and that kind of thing. Yeah, so yeah, both a concern, but especially Europa Clipper.
Any other questions here in our local audience, and then anyone online?
See another one in the chat.
Okay. Well, I checked and I realized that we are broadcasting on YouTube also.
Yep.
That's awesome. I'm glad for that. So I look forward to going back through the recording and just checking out some of that. There's a lot of information, but it's awesome stuff. So thank you so much. We're very grateful.
Thank you. I'll stop sharing.
Can you hear us applauding over here?
No, but I'll believe you. Thank you.
Okay, yeah, I didn't think it would come. Yes, we were all applauding and shouting and wanting your autograph. But anyway, thank you so much, Dr. Molyneux.
Thank you. All right, I'll turn my video off.
Guess we're wrapping up then.